Our invited speaker to start us all off is Charlotte Ward, who is faculty at Penn State, and she's going to be telling us about multi-survey modeling to characterize transients and galaxies.
Can everyone hear me okay? Yeah, great. So I am going to talk about Scarlet 2, which is a framework that we've built for pixel level, image level modeling of transients and their host galaxies across imaging data from any survey that you are interested in, whether it's Rubin, LS4, Euclid, or something else. Okay, so the goal of this work is to address science cases where we can really benefit from jointly modeling data from multiple surveys at once. And there are a number of reasons that we want to combine the data of these various surveys because they offer us different things. We have really deep space-based imaging from Euclid and soon Rubin that will help us to resolve the host galaxies of transients and deblend these crowded fields that are very blended in ground-based imaging. But we also have these great multi-epoch ground-based surveys like Rubin and LS4 that will give us sensitivity to transient fluxes over 10 orders of magnitude between them. And we also have access to both optical and infrared SEDs across these various surveys. And because there's a lot of coordination, especially when it comes to deep drilling fields, as well as wide fields overlapping naturally, we're very lucky to have these very large swathes of the sky where there is imaging data from multiple surveys that can help us. So the context for this work was actually a little bit more of a cosmological focus. So we wanted to address a particular challenge when we're producing good galaxy catalogs, that once we move from the depths of SDSS to the Dark Energy Camera Legacy Survey and then to Rubin-like depths shown here, we have a situation where in the 10-year coads of Rubin, over half of galaxies will be blended with other galaxies because of the ground-based point spread function. And you can imagine if you're trying to create a good galaxy catalog here, whether it's for your large-scale structure, whether it's for weak lensing, or whether it's because you care about the host galaxies and transients, we really want to have a good handle on how many galaxies are there, what are their accurate SEDs so we can get good photometric redshifts, are there any background interloper galaxies that are blended with these foreground galaxies? And the way that we can address this challenge of this blending and ground-based imaging that's very deep is to jointly model that imaging with space-based data as shown on the right. So you can see that once we have imaging from something like Euclid, we are able to resolve just how many sources are in that blend, what their shapes are, and then we can do a much better extraction of the SEDs from Rubin, as well as understanding the relationship between transients and their potential host galaxies. So just a few of the science motivations that drive this from the time domain side. We're really interested in identifying the preferences for transients to be in particular host galaxy environments, whether it's questions like why do tidal disruption events tend to prefer these Green Valley host galaxies? Do they like post-merger systems? Whether it's understanding the dependency of supernova 1A light curve shape on the local metallicity or something else about its local environment, whether it's about understanding the preferences of different kinds of superluminous supernovae, whatever it might be, we want to have a framework that can easily extract the local properties of host galaxies as well as their more global properties. We also want to have a framework that can produce transient photometry without reference images. There are two situations where this is particularly useful. If you want to produce light curves across optical and infrared surveys without worrying about whether your reference images are matched up correctly, particularly important for AGN, but also in the early survey where your transients are in those references, you can use this particular approach. And you can also deal with situations where you maybe just have one image with a transient and you want to use constraints on that galaxy in the background to extract photometry without needing a reference. So the approach that we adopt in order to be able to achieve this is what is often called scene modeling. That's how it's been referred to in some of the previous talks this meeting. And the idea is that we have an internal model of the sources in the sky. What are their colors? What are their shapes? What are their positions? But we also have a model of each of the input observations, regardless of what survey they're from. For each observation, what pixel grid is it on? What is the WCS, the pixel scale? What is the point spread function? And then we do a forward model where we take our internal hyper-resolution model, render it using the knowledge of the observation, and then we can do our fitting in pixel space, and we can just throw in any observations, regardless of whether they're matched up on a pixel grid, have different PSFs, different bands and everything. And this is the way that you can do this. So these are some of my lists of reasons why you might want to pay attention to me if you've ever been in situations where this could be useful. So the big one is the host galaxy catalogs. If you want to be able to identify faint background host galaxies that could be alternative hosts to the apparent hosts in the foreground. If you want to get good photometric redshifts by extracting optimal SEDs, whether you want to resolve substructures within the hosts. I talked about the multi-survey photometry without reference images. If you want to have a kind of forward modeling approach to get MCMC sampled posteriors on particular parameters you might really care about for an individual transient, maybe it's the position, maybe it's something about the host. And if you ever want to extract photometry from very blended ground-based imaging, a good example of this is if you have lensed quasars or supernovae, where they're very blended in the ground-based imaging and you can't get your 10 epochs of HST that you want, you can extract it across those data sets. And if you want to have a scene modeling approach for highly precise 1A photometry by treating the SED dependence of the PSF in the forward model. So these are just some situations where you might want to consider this approach instead of the data products that are already available through difference imaging. So as I mentioned, we have these additional challenges in the era of Euclid and Rubin, because as we go to these space-based resolutions, the typical surface profiles that we would use to model galaxies don't really cut it anymore when you look at all the complex substructure that we see in Euclid and Rubin. So we need to switch gears and instead use non-parametric galaxy morphology models, right? We're not assuming surface profiles or anything like that. And in order to do that, you have a computational challenge where you've lost a very convenient constraint that galaxies have these simple profiles. So then you need to use machine learning in order to stabilize your fitting. And this needs to be fast. If we want to get scene model photometry of every 1A supernova, or if we want to get galaxy catalogs across the full Euclid and Rubin dataset, we need to use GPU acceleration. So Scala 2 was built to achieve all of these things. The goal was to use score-based neural network priors on galaxy morphologies in order to treat the complex galaxy shapes that we're seeing in our Euclid and Rubin. You can see the documentation here, and it's also been built for transient science. Just to explain how the priors on the galaxy morphologies work. So we have score-based neural networks that are trained on images of galaxies. We have a range of different training sets that we've used, LSST-like imaging, imaging based on simulated higher resolution data where we can understand the changes in the galaxy morphology across the infrared and optical. And we use this approach to stabilize the fitting. And the way that we do this is if you have a shape that, a galaxy shape that the prior has not seen, it adds a really strong term for that particular pixel in the gradient in order to fit that galaxy shape. And this allows us to avoid hard constraints on galaxy shapes and the numerical instabilities that result, and instead help guide the fitting to come up with realistic galaxy shapes when we're in this non-parametric regime. If you're ever worried about how much did your prior affect your transient host galaxy shape, for example, you can use this hallucination score metric to understand for each pixel how much the prior was used in order to infer the galaxy properties instead of the data. We often are in situations like this where we have a very complicated shape, low surface brightness galaxy, and we want to model the different components. I have in mind, for example, if we have a transient in some substructure that we want to extract the SED of locally, we can use this wavelet decomposition in order to map out the different scales on different, the different structures on different physical scales so that you can extract detailed information about substructures within the galaxies. And of course, we can extract light curves. So if you throw in your 1,000 LSST images along with your 2 Roman epochs, for example, you can anchor your galaxy morphology model on that space-based image, but extract photometry across all of the ground-based data. So these are kind of a summary of what you can get out of your multi-survey fit. You can also deal with things like whether your astrometry solutions are misaligned or not quite right between the 2 surveys. It can also treat things like that. You can get posteriors on transient parameters that you care about, as well as your light curves and some morphology models. Just to show this in action on some of the early data. So here are some early Euclid images from the Q1 data release and some of the early Rubin images from DP1. And you can see that we're modeling this particular supernova host galaxy across the different optical and infrared images with the forward model. Here are some examples of some of these supernova hosts where you can see that we do have fairly detailed substructures that we need to be able to model with this non-parametric approach. And we've shown that the SEDs, particularly in the early data where there's a lot of transient contamination, are improved. And this is just showing why you want to do this joint modeling approach across the surveys. We just have the host morphology models of a few galaxies above from Rubin imaging only. These are very faint. They're smeared out because of the ground-based PSF. But once you jointly model them with Euclid, you can really see the complicated substructures and understand where is your supernova within that galaxy. One of the other challenges that comes with combining data sets from different surveys is that there's a lot of resampling involved, whether you're working with coads, where that resampling to make the coad has created correlated noise, or you're warping all of your images to the same WCS to make your code faster. We often get situations like this where we have this very lumpy kind of background correlated structure. And we've added a way to treat this so that Scarlet 2 will treat all of that for you by measuring the power spectrum of that structure in the background and incorporating that during the fitting too. And this is just showing it in action on some transients and on some coads in the Rubin Science platform. One of the challenges with Scarlet 2 was the usability. So it's really tough because you need to really have a good understanding of your, your observations, what are your PSF models correct and all of that, and how to set up the problem for your particular science case. There are a lot of different science cases that we want to be able to address. So with the help of link frameworks, we've built this interactive questionnaire where you can kind of put in, this is the data I have, this is what I want to get out of my model, and it can give you snippets of code in order to build something for your science case. We've also added these validation suites with the help of Link in order to understand if there are any problems with your input observations. Maybe your PSF model isn't quite centered or something like that. And it can identify those issues early for you using this validation. So a question I often had as we were developing this over the last few years is how fast is it? Is it easy to run this on the whole Euclid and Rubin coad data set or run it on every supernova? And for a long time, I didn't really know how to answer it because things were kind of slow when I was testing it out. But due to a lot of developments over the last few months, I can now confidently say that this is fast enough to run on every transient if we have a large cluster where we can store all the data relatively efficiently. This is a particular example. Let's say you have a supernova, 1,000 cutouts across Rubin and a few space-based images to incorporate in the forward model. We have a prescription shown here where you can do oversampling to a common pixel grid and then forward model across them while treating the correlated noise that comes out of the resampling. And you can do this in less than a minute on your laptop. So you can imagine that we could scale this up if we wanted to. I wanted to show some science examples of how we're applying this so far and really kind of stress testing the code for different science cases. One of the examples that we think will be really interesting is looking for wandering massive black holes from both tidal disruption events and from AGN that have low levels of variability. And in particular, we want to be really sensitive to small spatial offsets between that massive black hole and the host nucleus. This is why this forward modeling approach with the space-based imaging, but also the variability information could be quite powerful. So we want to test cosmological simulations that predict that once we get to relatively low masses, dwarf galaxy regime, that we expect the majority of massive black holes to not lie in their galaxy nuclei, but to be wandering around the outskirts as a production of their merger history. So I encourage you to go see Kendall Sippy's poster about the pipeline they've been building in order to detect these with Rubin and Euclid. And I wanted to point out some nice work by Yuhan Yao, who found the first spatially offset tidal disruption event from a wandering massive black hole, shown here. The ZTF imaging above was where she first identified that this was likely a spatially offset tidal disruption event, not in the galaxy nucleus. It's always a little bit hard to convince attack when you're requesting follow-up from these images above that it is indeed a candidate for an offset TDE. So Scarlet 2 was able to do detailed sampling of the relative positions in order to confirm that offset. And then Yuhan got all this amazing follow-up with HST, Chandra, and the VLA to show this was indeed a tidal disruption event from a 10 to the 6 solar mass black hole wandering 0.8 kiloparsecs out from a host galaxy with another 10 to the 8 solar mass black hole. Another thing that we want to apply it to is producing these multi-survey light curves of AGN. AGN always there, so reference images can always be a little bit fraught. So this is a framework for us to deblend the AGN in the host and to get out light curves across multiple surveys. And we're hoping to apply this to the detection of changing look AGN across long baselines. And I would encourage you to check out Miranda Zach's poster on her work in developing a framework to identify changing look AGN based on that photometry. On the AGN topic, we're really interested in looking for populations of low mass AGN in dwarf galaxies. And in particular, we want to get really accurate SEDs of those dwarf galaxies in order to estimate the masses. So this is some work where we've been looking at getting accurate SEDs of faintly variable AGN in dwarf galaxies, and where we're interested to do population level modeling of the low mass end of the black hole to galaxy mass relation with populations of AGN in Rubin. And then a particular example, which was quite a challenge for Scarlet 2, but it's now working well after some hard work by my student Bina Krishnaraj, is to extract accurate time delays from light curves of strongly lensed supernovae and AGN. In Rubin, we expect a lot of situations like this, where the separation between the multiply imaged supernovae, or AGN, are highly blended in the ground-based Rubin imaging. We expect the typical separation of strongly lensed multiply imaged supernovae to be kind of about 0.6 arc seconds. So if you want to extract light curves, you want to be able to treat that blending. And we can do this by having a single epoch of space-based imaging and using that to extract all of the deblended photometry across those blended Rubin cutouts. So here are some examples of this. Bina made these simulations of what the population of lensed 1As we expect to detect in Rubin looks like in both Roman and Rubin imaging. You can see examples of this here. This is a typical system where it's highly blended in Rubin, but a space-based epoch tells you what's going on. And then she's been running Scarlet 2 and extracting light curves from Rubin images like this, where you can see that it's very hard to distinguish between the different sources. But if you have this one epoch of space-based imaging to tell you about the lens and the positions of the supernovae, that you can extract photometry. And these are some of the light curves that she's been producing and some of the time delay estimates. And she's been showing that this pipeline works very well across the surveys. So this is my summary of what Scarlet 2 is. So we're hoping that this is a framework where you can really combine any imaging data, whether it's a single JWST image that you got, along with 1,000 epochs of Rubin imaging, and extract light curves, extract post-morphology models, understand the properties of background galaxies that could be alternative hosts. There are various situations where we want this to be useful. We're kind of finalizing the structure of the code now. I mean, it's all working. It's well documented. But if there's any other features that would be useful for your science, please let us know now so that we can make sure that that is incorporated. And I think I'll just leave up my answers to the questions from the organizers here in case anyone wants to read through. Great.
Okay, thanks, Charlotte. We got lots of time for questions. Questions for Charlotte. Nevin.
So utilizing for AGNs light curves, that seems amazing. That's really like very useful and smart application. I wonder, your Hubble image is obviously not in the same band as probably AGN or Galaxy. You have to do some interpolation of some sort to extract AGN, right?
Yeah, that's right. So essentially what it would do is it will have information about the galaxy shape from the highest resolution image where it is well separated from the point source. And it's using that to kind of, that will be most informative in the forward model. Because you have different bands across your very blended ground-based imaging and your higher resolution space-based imaging, you will need to add some assumptions about how that galaxy shape looks different across the SED. And Benjamin Remy has been building a prior that is basically trained on galaxy images across various wavelengths so that it at least has some constraints on that when needed. But the idea is, you will be able to get well-sampled posteriors on any uncertainties that arise from, difficulties in the deblending. So it will just do the best it can with the data sets you have and use all of that information.
Kostya?
Thank you. Great talk. Do you have any plans to deliver it maybe as an on-demand service to brokers or to science platforms?
Yeah, that's a great question. So I think Gotham is probably the best person to talk about that. So we've been talking about it would be great to have it as part of BLAST. I mean, my dream is that pretty much whenever any of this aspect of your analysis or you want to add in any data from, the other surveys, you could just kind of click a button or something and it would show you, okay, this is the best SED model and host model and light curve that you can get. So I think it would be great to have this as part of some online interfaces where it will provide that on demand. So that's kind of in the works now that we've finished the code. And then we're also, in the meantime, making a bunch of Jupyter notebooks that you could run on the Rubin Science platform, on the Nexus, things like that, if you just kind of want to do it yourself in the meantime.
Vivek, do you want to ask online?
Yeah, am I audible?
Yep, we can hear you.
Yeah, so I'm just curious about whether Scarlet 2 takes into account the intrinsic variability seen in a type 1 AGN while modeling the profile of the host galaxy.
The what variability of the agent?
The type 1 AGN are intrinsically variable on long-term scales, right? So does Scarlet take that variability into account while modeling the host profile?
Oh, yes, definitely. Yeah. So what you're doing is you're modeling a variable point source in addition to that host galaxy, and it's deblending the two. And you just tell Scarlet 2 that you expect a variable source there, and then it will treat the variability and give you a light curve as well.
It assumes the galaxy is static.
Yes. Having said that, you can let the galaxy vary if you want, but I wouldn't recommend it. Maybe if you have light echoes or something, you could do that.
And who's the other one online? Lucas? Online?
Yes, hi. That's amazing stuff. Have you tried the Scarlet 2 on, just the basic kind of crappy ground-based bad seeing data, imaging data?
Yeah. Oh, I run it on ZTF.
I mean, even crappier.
I'll give you Palomar Quest data, then we'll really see.
Yeah. But yeah, long story short, yeah, it works fine. The main challenge with ZTF, for example, is the undersampled point spread function. But it is, modeling the fact that your PSF looks totally different and can be very large on, each single exposure. I've been running on ZTF the longest. And yeah, it's built for that.
Great. You should say in the interests of bias that there are other crappy ground-based surveys out there.
ZTF is great.
Yeah.
Hi, you may have mentioned it and I just missed it, so please tell me if that's the case. You mentioned that you take into account the SED dependence of the PSF when you're doing your forward modeling. I was just wondering, how did you either determine the SED or what assumptions did you make about the SED? And based on those assumptions, how much did that matter for your final result? If that's something you checked, I'm just curious.
Right, so it's all being fit in the forward model simultaneously. So you're fitting the SED at the same time as you're fitting the PSF. So it's just marginalizing over everything at once. And you can either set the PSF to be fixed or not. But having said that, you could, I haven't tried this very much, but you could add priors on SEDs and things like that if you wanted as well.
Got it, thank you.
Jakob?
Turning to the case of crappy ground-based data. This is looking very nice. Have you tried including nearby field stars to model them and tie them to some sort of photometric system?
I have not. Yes, usually I'm just modeling them out, or we could fit all the stars, but I haven't done the photometry with them.
Allows you to quantify repeatability and all that stuff.
Yeah, that'll be interesting.
Ashish?
Great initiative. I had a question that is somewhat related. So if you have a new point, a new transient where the image that you have access to is really small, are there any issues that can come up with that? And has that been quantified in some way?
So in this situation, you're imagining you just have a cutout.
Yeah,
and
tiny stamps.
Yeah, so the main thing is you just need to have a good PSF model. So, if you're building your own PSF model, that tiny field will be a problem. But if that's produced as part of the data products, which it usually is, then you're fine. The other thing is, if your astrometry solution is poor and you don't have many other sources in the field to help fit it, and you let it fit for the astrometry, then it's degenerate. But if you just make your cutout big enough so that you can refit the astrometry with the other sources, then that's all fine. So you would basically set your free parameters based on how much information you have.
One last quick one, Eric.
For the lens transient searches, is it sensitive to when the epoch of the space-based image is taken, if like some of the lens images are there or not?
Yeah, I'm glad you asked this, because for a while I thought that you must surely have to have your epoch of space-based imaging has the positions of the transients, right? But what Vina has been finding is she's been testing where you have your space-based epoch just before to help anchor just the morphology of the lens and the host versus the one that also tells you the supernova positions. In most cases, it doesn't actually matter as much as we expected. And that's pretty much because what it's doing is it has these 2 or 4 or whatever floating point sources, and it's finding what is optimal across the different images. So they just kind of float around and they usually find the right positions, unless it is fully degenerate. You know, the degeneracies will just come out in the error bars. But for the situations like this level of blending, it's working without having the epoch of space-based imaging having the supernovae. So we're hoping that this will be useful for survey level lensing, where you couldn't get your HST stuff, but maybe if you just have your Roman image of what the system looked like beforehand to anchor the background modeling, that could do the job in cases like this anyway, based on her tests.
Okay, well, let's thank Charlotte again.